Welcome back. Video 2 of 5. This is where the mathematics begins. Linear algebra, the language every neural network is written in. We'll climb the dimensional ladder from scalars to tensors, master matrix multiplication, tour the 17 types of matrices and learn to measure vectors with L1, L2 and L infinity norms. Everything comes with real-world anchors, taxis, crows, and Spotify playlists included. Let's get into it. Welcome to part 1 of the unit linear algebra, and before you groan, let me sell it to you. Here's the single most important sentence of this chapter. A neural network is nothing but tensors flowing through matrix multiplications. That's it. That's the whole secret. Which means linear algebra isn't background math, it is the language deep learning is written in. Learn these objects and every deep learning paper becomes readable. Our route will climb the dimensional ladder from scalars to tensors, master matrix operations and the matrix zoo, measure vectors with norms and finish with the 3 crown jewels: eigen decomposition, singular value decomposition, and principal component analysis. Every abstract object will come with a real-world anchor. I promise it's friendlier than it sounds. Let's go. We start dimensional ladder 8-0. The scalar. A scalar is just a single number, that's all. It has a magnitude, a size, but no direction. Temperature, 36.6 degrees. Your age, the price of a coffee. Each one is a scalar. The real-world analogy is the thermometer. Its reading is just one number. In notation we write scalars as simple lowercase letters like x equals 5. Now, why should a deep learning student care about something so simple? Because scalars are everywhere in training. The learning rate is a scalar. The loss value your network reports every epoch scalar. A single pixel's brightness scalar. Here's the ladder we're climbing: scalar, then vector, then matrix, then tensor. Each rung just adds one more axis. Keep that picture the next 3 slides. Climb it. Rung 1 or the ladder, the vector. A vector is an ordered, one-dimensional list of numbers, and that word ordered is doing real work. A student scores 85, 78, 92 mean maths, physics, chemistry in that order. Shuffle them and you've changed the student. There are 2 ways to picture a vector, and both are useful. The physics view an arrow with magnitude and direction, like a velocity or 60 km/h east and 45 north. The data science view a list of features describing something. Deep learning mostly uses the second view, and here's a beautiful example. Spotify represents your music taste as a vector of a few hundred numbers. When Spotify says a playlist matches your taste, it literally means your vector and the playlist's vector are close together in space. Similar taste equals nearby vectors. Word embeddings do the same thing for words. Rung 2, the matrix, a 2-dimensional grid or numbers, arranged in rows and columns. Look at the example on the right. 3 students, 4 subjects, a 3x4 matrix or scores. And there's our convention, the one students mix up constantly. ROWS first, column second. 3x4 means 3 rows. Say it like RC rows, columns like RC cola. Sounds silly, works forever. Matrices are everywhere once you look. A grayscale photo is a matrix. Every entry is a pixel's brightness. An Excel sheet of customers and their features matrix. The weights of a neural network layer matrix. But here's the deeper idea I want to plant today. A matrix is not just a table or numbers. A matrix is a machine that transforms vectors. It can rotate them, stretch them, squash them. Hold that thought. When we reach eigen decomposition, it will bloom. And rung 3, the top of the ladder, the tensor. A tensor is a multi-dimensional array, and here's the neat part: scalars, vectors, and matrices are all just special cases. A scalar is a 0D tensor, a vector is 1D, a matrix is 2D. Tensor is the family name. Where do we need more dimensions? Images. A color photo has height, width, and 3 color channels: red, green, blue. That's a 3D tensor. A 100x100 color image is a 100x100x3 block of numbers. Video adds a 4th dimension: frames over time. And a training batch or videos, 5 dimensions. Try this on yourself. Your phone shoots 30 frames per second at 1080 by 1920 resolution in color. What's the tensor shape or 10-second clip? 300 frames by 1080 by 1920 by 3. And now you know why Google named its library TensorFlow, tensors of data flowing through the network. That's deep learning's entire data model. Let's put the whole ladder on one slide because this picture is a guaranteed exam question. Scalar 0 dimensions 1 number, in deep learning the learning rate, the loss value, vector 1 dimension, an ordered list. In deep learning a word embedding, 1 samples features, matrix 2 dimensions rows and columns. In deep learning a layers weights, a grayscale image, tensor any number or dimensions. In deep learning color images videos batches, when the exam asks you to define these and it will the difference between a pass answer and a top answer is those deep learning examples. One definition, one example each. That's the formula. Now we start actually operating on these objects. First up, matrix times vector, and I'd argue this is the single most important operation in all of deep learning. The mechanics, a matrix A, or size m by n, multiplies a vector x of length n, and produces a new vector y of length m. Each output element is the dot product or one row of A with x. In other words, a weighted combination of the inputs, and the dimension rule. The matrix's column count must match the vector's length, m by n times n gives m. The inner nes must agree. Now here's the payoff, and it's on the slide in the green box. One layer of a neural network computes W times X plus B weights matrix times input vector. That's THIS. A forward pass through a network is just a chain of matrix vector products. When you hear a GPU is fast at deep learning, this is the operation it's fast at. You now know the atom. Next, matrix times matrix. Same spirit, one extra rule to respect. Two matrices A and B can be multiplied only when the number of columns in A equals the number of ROWs in B. If A is m by n, B must be n by p, and the result C is m by p. I say it as a chant: inner dimensions must match and disappear, outer dimensions survive. Try these in your head. 2 by 3 times 3 by 5, valid result is 2 by 5. 3 by 2 times 3 by 2 / invalid. Inner numbers 2 and 3 don't match. 2 warnings before we move on. First, matrix multiplication is not commutative. A B and BA are generally different, sometimes one isn't even defined. Second, a practical gift: when your deep learning code crashes with a shape error, and it will, just write the shapes side by side and check the inner numbers. Shape errors are the number one beginner bug, and now you can debug them on site. Every number system has a 1 and a reciprocal. Matrices do too. The identity matrix, I, has 1s on the diagonal and 0s everywhere else. Multiply any vector by it and nothing changes. It's the matrix version of multiplying by 1. The inverse of A, written to the -1, is the matrix that undoes A inverse times A gives the identity. Encrypt then decrypt. Zip then unzip. Do then undo. Why care? Because inverses solve equations. If Ax equals B, then x equals A inverse B. One multiplication, solved. But in this matters not, every matrix has an inverse. A matrix with no inverse is called singular. My favorite analogy: it's a blender. Once you've blended the smoothie, you cannot unblend it, the information is gone. Keep x equals A inverse B in your pocket. At the very end of this unit in linear least squares, it comes back for its encore. There are 17 standard types of matrices, and we'll tour them like a zoo in 3 visits. First visit: classification by pure shape. The singleton matrix, just one element. The null matrix, or zero matrix, all elements 0. The row matrix, 1 row, any number of columns. And its twin, the column matrix, 1 column, many rows. Fun fact: a row matrix is exactly how one data sample is stored in your dataset. Then the shape family: horizontal, wider than tall, more columns than rows. Vertical, taller than wide. Rectangular, any matrix where rows and columns differ. And finally the square matrix, rows equal columns. Remember S1 especially because square matrices are the stage where all the big drama happens. Determinants, inverses, and eigenvals all live there. The names really do describe themselves. That's the good news about this zoo. Second visit to the zoo: square matrices with special patterns inside. The diagonal matrix, everything 0 except the main diagonal. The scalar matrix, a diagonal matrix where all the diagonal entries are the same number. And the identity, a scalar matrix where that number is 1. Notice the nesting there. Identity is a special scalar matrix which is a special diagonal matrix. Like Russian dolls. Quick check, is the identity a scalar matrix? Yes, all diagonal entries equal 1. Is every scalar matrix an identity? No. Diagonal fives don't make an identity. Then the triangular family. Upper triangular, everything below the diagonal is 0. Lower triangular, everything above is 0. Why do computer scientists love triangular matrices? Because equations with them solve almost instantly by simple back substitution. Fast solvers in every library factor big matrices into triangular pieces first. Structure equals speed. Final visit to the zoo, and these three are defined by how a matrix relates to its own transpose. Remember, transpose means flip rows and columns. The symmetric matrix, a transpose equals the matrix mirrors perfectly across its diagonal. Star fact, every covariance matrix is symmetric, and that's the matrix PCA is built on. We'll meet it soon. The skew-symmetric matrix, a transpose equals minus a transposing flips every sign. And here's a classic exam proof. In one line, each diagonal entry must equal its own negative, so the diagonal must be all zeros. Beautiful, right? And the orthogonal matrix, the gold of numerical computing. Its transpose is its inverse. A transpose gives the identity. Geometrically, these are pure rotations and reflections. They preserve all lengths and angles. And practically, inverting one is free, just transpose it. Remember orthogonal especially. In singular value decomposition, the U and V matrices are exactly this type. New question: how big is a vector? Sounds trivial, it isn't. A norm is a function that takes a whole vector and returns a single non-negative number measuring its size, its length, its distance from the origin. And here's the twist: there isn't one norm. There's a family. The L1 norm, also called Manhattan, the L2 Euclidean, the L infinity, the max norm. All of them come from one master formula, the PE norm. Plug in P equals 1, 2 or infinity, and out pop the family members. Let me give you the running example we'll use for the next 3 slides. Take the vector 3, minus 4. Its L1 norm is 7. Its L2 norm is 5. Its L infinity norm is 4. Same vector, 3 different answers for its size. So which is right? All of them. Choosing the norm means choosing what big should mean in your problem. Machine learning uses norms for distances, for errors, and for regularization, and each job picks its own norm. Let's meet them one by one. First family member, the L1 norm, and its nickname tells you everything. The Manhattan norm? The rule: add up the absolute values of every element. For our vector, 3, minus 4, absolute 3 plus absolute 4, 7. Why Manhattan? Picture a taxi in a city grid. To go 3 blocks east and 4 blocks south, the taxi cannot cut diagonally through buildings, it drives all 7 blocks. The L1 norm measures distance the way a taxi experiences it. Now, the machine learning superpower. L1 is used in lasso regression for regularization, and it has a magical property: it pushes small weights to become exactly 0. Not tiny 0. The result is a sparse model where useless features literally switch off. Built-in feature selection for free. Why does that happen? The absolute value penalty pushes with constant force, all the way to 0, never easing off. Keep that in mind, you're about to see the contrast. Family member to the L2 norm, the Euclidean norm. This is the one your intuition already knows. The rule: square every element, add them up, take the square root. It's Pythagoras generalized. For 3, minus 4, 9 plus 16 is 25, square root, 5. Remember, the taxi drove 7 blocks. The crow flies straight over the buildings 5. Same 2 points, taxi versus crow, L1 versus L2. This is the default norm. When a paper writes a norm with no subscript, read L2. It powers mean squared error ridge regression, k nearest neighbors, it's everywhere. And note the personality difference from L1. Because of the squaring, L2 punishes large elements disproportionately. One huge weight costs more than many small ones. SOL2 regularization shrinks weight smoothly toward 0, but rarely exactly to 0. L1 creates sparsity, L2 creates smallness. 2 tools, 2 effects. And the third member, the L infinity norm, the worst case norm. The rule is almost embarrassingly simple: take the largest absolute value and ignore everything else. For 3, minus 4, the answer is 4. Only the biggest coordinate matters. When is that the right way to measure? Whenever the worst case is what matters? Here's an example that makes it visceral. A medical dosing device has errors across 3 channels, 0.1, 0.2 and 2.9 milliliters. The average looks fine. But L infinity screams 2.9, and that's the channel that could hurt a patient. Bridges are rated the same way by the weakest beam's worst load, not the average. So our running example ends, same vector L17, L25, L infinity 4. Notice they always come in that order: L1 biggest, L infinity smallest. That ordering is a handy sanity check, and it's about to earn you quiz points. Let's line all the norms up side by side. This table is your revision card. L1 Manhattan, sum of absolute values, the taxi on the grid 7 4-hour vector, used in lasso and sparse models. L2 Euclidean, square root of the sum of squares, the crow flying straight, 5, used in mean squared error ridge and k nearest neighbors. L infinity, the max norm, largest single element, 4, used for worst case bounds, and the general p norm ties the family together. P tunes the geometry smoothly between them. One pattern to lock in for any vector whatsoever: L1 is at least L2, which is at least L infinity. 7 5 4, always descending. If an exam option violates that ordering, you can reject it without computing anything. Which brings us to exactly such a quiz. Quiz 2 norms. Here's the vector -6, 8. Which statement is true? Option A, L1 is 10, L2 is 14, L infinity is 8. Option B, L1 14, L2 10, L infinity 8. Option C, L1 14, L2 10, L infinity 6. Option D, L1 to L2 10, L infinity 8. Before you compute, remember the ordering trick. L1 biggest, then L2 / then L infinity. One of these options breaks that law and can be rejected on sight. The numbers are friendly, no calculator needed. Pause the video now and work it out. And the answer is B. L1 is 14, L2 is 10, L infinity is 8. Let's verify together. L1 absolute -6 plus absolute 8, 6 plus 8, 14. L2 36 plus 64 is 100 square root 10. A perfect 6, 8, 10 triangle. Pythagoras smiling at us. L infinity, the bigger of 6 and 8, 8. Now the elimination trick in action. Option A claims L1 is 10, but L2 is 14, L2 bigger than L1. Impossible. Rejected without any arithmetic. And option D, L1 equals 2. That's the classic trap. Someone computed -6 plus 8 and forgot the absolute values. If that was you, no shame, just never again. Norms done. Next stop, the crown jewels or linear algebra. If this lecture helped you, do like, share and subscribe to Shri Tech Bytes for more lectures like this one. See you in the next video.